In this part of the video, we first introduce a particular kind of decision tree building algorithm and the principle behind the algorithm, that it is the information gain, which is in turn based on the entropy concept we just introduced. And later, I will tour you in some Python coding about how to calculate entropy for a particular distribution in the sample case. If you are an undergraduate student in this subject, you might want to pay more attention at this part, because implementing ID3 is one of two options for assignment 2 for students who took subjects 31005 that are undergraduate students. ID3 algorithm is a way of constructing decision trees, and the pseudocode of the algorithm has been provided with the learning material of this week to UTS Online. The essence of this algorithm, there are two pieces of essential points of the algorithm. One is the recursive construction of a data structure, but this part shouldn't be challenging too much, because that is reflected in the structure of the pseudocode. Even that is the pseudocode, you will get the most of this part of construction, because it is the structure that counts in this algorithm. And the second piece of essence is the evaluation of data attributes, which we will use to construct or recursively construct the decision trees, and which we need the computation of information gain, and in turn the computation of entropy, which we will discuss right now. Now let us have a look at the algorithm. The first part of the definition of the function of constructing ID3 decision trees, of using ID3 algorithm to construct decision trees, is to specify stopping conditions of this function. Look, if when the input of the function accepted shows that all the target values are belonging to one particular classes, or there is no attributes to exploit, the function returns a leaf node. That means the recursion must be ended, and the decision tree has arrived its leaf node. And these are represented by the three return statements in the pseudocode. When there are more branches to build, the algorithm builds the branches according to the best attribute of the observable part of the data, and the criterion of attribute to be best is that when we split the data set according to the value of that proper attribute, the split will result in most information gain. And what is the information gain? Information gain is defined as the difference between the entropy of the original population and the summed entropy, the summation of weighted entropy of the subpopulations. If the original set of training examples to be S, and we split S into different subsets, we call that S subscript V, and V belongs to the value of a certain attribute. We first calculate the proportion of such a subset in the original set and use this proportion to weight the entropy of the subgroup, a subset of samples of S substitute as subscript V. If we think about it more carefully, the reason we are able at all to compute such difference is that we think a good attribute will result in entropies in the subsets that are smaller than entropies in the original set. We know this is because in our previous analysis, we know that entropy decreases or reduced with the purity of the set. So if we are able to split the training set into subsets, and in each of those subsets, the distribution of the target values is more pure than the previously mixed distribution of the target value, we will expect a large difference between the original entropy and the weighted entropy sum. Or we can say we expect to gain information by such a split. In the following, I will demonstrate the construction of entropy computation program in Python, which is the essence of implementation of an ID3 decision tree building algorithm. So let's consider a very basic example. Let a set of events to be A, one B, see another A, another maybe B. Now we have a set of events consists of 3 A's and 2 B's. Consider that this is representation of a stochastic population between A and B, and that means we consider that A and B appears randomly, and now is an implementation of the appearance. So we first need to calculate or to estimate the probability of event A according to its frequency. So to do this, it is obvious we have 3 A's in S, but let us do this in a more principled way. As before, we can compare S element wise with A. Okay, let us use an NumPy array to wrap this object. So those arithmetic and Boolean operations will be better supported for the collective operations. But instead of calculating the trues and falses manually as we previously done, we can now use a functionality of NumPy that is none other than just state or purpose count non-zero. Okay, that function non-surprisingly will count how many true values, how many correspondence between the set and event A. Oh, okay, that is 3. Let's call it an A. Of course, we can have another NB. Let's say B, the frequency as the number of S equals to B, and MB. See what we have. Good, as expected. But to calculate the entropy, we will need the probability. Let's consider what is the probability will be represented here. The probability will be calculated as fraction between number of A and total number of the set S, or we can call it the cardinality of S, and let PA to be approximated by Similarly, we can compute PB to be this. This is what we have already done. And to get the entropy, let us spell out the definition of entropy. But here, because we have only two kinds of events, we can explicitly write summation without going to the loop style representation. That is to be logarithm. Remember that it's based on 2, and that is inverse PA. So we take the inverse back, we will get this as number of A, call it NA. Second part is to calculate average how many bits we need to describe event B. So that would be our entropy. Okay, let's just do this. Let entropy equals okay, and we need to substitute PA here. Let PA to be float A. B. And the entropy can now be calculated according to the equation. Log, we need this function log 2. Okay, and that is inverse of the probability, and here is what we use. Well, seems to be some reasonable number. Okay. Now let us summarize the operation into some functions that we can define and reuse later. So the trick to do this is to generalize the operation into some input set, which elements we do not prescribe ahead. Let us define the entropy calculation. Get entropy. Let's allocate this variable for our entropy. Okay, so because we do not know the elements, the members in the population of S, so when we get that, we got call it different classes in S. Unique S. Have a look at this. It gives different elements as contains, and it ensures each element appear in the result set only once. So we can now for each C in C calculate its contribution into the entropy. Let P equals, we can copy this part here, and we consider when S equals C underscore, let us calculate the probability. Okay. And now let us increase entropy by the contribution of this particular event. Power 2. Good. Now we have the function of computing entropy. That is test our function. Good. Oh no, we haven't defined it. Execute and define the function. Oh, we need some input. Okay. Well, exactly the same as expected. Good. Say for another example, let us add another event. We would expect the entropy to be a little bit more than the previous one, because now we make the situation more complex, and assumably we need more bits to describe this situation. Okay, in this case, let's try. We do not need to redefine this function, because this function should work for whatever kind of input sets. As expected,